Okay, welcome back to the video lecture series on network theory. This is lecture number 49. And we are into module number 4. Okay, so last class we just started with the Laplace transform, right? So there we have just discussed about why Laplace transform is being used and how to use the Laplace transform mathematically. So we have seen around for 5 functions, right? So we shall continue the same. Okay. So before that, let me just quick. So we have taken these functions, namely, and their equivalent Laplace transform. So first one we started with the constant, right? So for constant we have seen the equivalent Laplace transform turns out to be 1 by s. So that means constant divided by s. Okay. And second one we have taken Laplace transform of t raised to n. So that turned out to be root of n plus 1 divided by s raised to n plus 1. Okay. And third one we have taken unit step function, that is u of t. Fourth one, shifted unit function by some amount, that is like t minus a if you take. So for that it will be e to the power minus as divided by s. And fifth one, I think we discussed about the unit ramp function. So that unit ramp function r of t, which was equal to t. Okay. So this was discussed and we arrived at Laplace transform of unit ramp function was 1. I think this is sixth one, right?
Yes, sir.
Delayed unit ramp function. Okay. So if you consider this delayed unit ramp function, so we already know that r of t is represented like this, unit ramp function. So delayed means so it is a ramp signal, but instead of starting at 0, it will start at some time value. Okay. So that time value, if you assume it as a, so that ramp will look like this. Okay. Now, if you consider the definition over here, so if you take the timeline, so here to here it is t greater than 0, right? And here to here it is t less than 0. But here if you consider one more thing over there, that is if you split this before 0 to a and after a, so this will be nothing but t less than a, but it is greater than or equal to 0, right? And here this entire area, it will be what? T greater than a. Okay, understanding this? So in this signal, so if you consider, so how to define the existing signal here now? Okay, but how to define this r of t minus a again? So r of t minus a, it can be defined as, it will be equal to t when t is greater than a and equal to 0 when t is less than a. Okay, understood this, everyone? Yes, are you all
Yes, sir.
following this
Yes, sir.
graphical rotation? Okay,
Yes, sir.
now if you take, we have in mathematics or in signals and systems, so there is a property, so that property is nothing but time shift property. Okay, so if you using time shift property, okay, that is nothing but, so already we know a Laplace transform of some function, say x of t, if you take, that will be something like x of s. So if you have a shifted version, something like t minus t naught, if you apply the Laplace transform to this, it is by time shift property, we will see it in the coming sections. So it is nothing but, it says that Laplace transform of time shifted version is given by e to the power minus s t naught into x of s. Okay, this is the standard property here. So in this place, what we have now, we have, instead of x of t, we have r of t, and in the place of t naught we have a. Okay, so if you apply the Laplace transform here, so directly you can write e to the power sa in the place of t naught divided by x of s. So x of s means, what is the Laplace transform of this x of s? That is x of t, in our case it will be r of t. It was 1 divided by s square, right? So this is going to give us e to the power minus sa divided by s square, where 1 by s square is Laplace transform of r of t. Okay, yes, is that clear now?
Yes, sir.
No need to
Yes, sir.
integrate here. We are just using the property. By using this property, we can write like this. Okay, so we will discuss this property in the coming class, so don't worry about this time shift property. For time being, you just remember that. Okay, so that was the example there. Okay, and next one, next function let us take the next one, that is seventh one, as unit impulse function. Seventh one is unit impulse function, which is denoted by delta of t. Okay, so it is graphically it is given like this. Okay, so if you have graphically, okay, so unit impulse function is the one which has a unity value at 0, and for rest of the value will be 0. Okay, so at 0 it will be have a unit value, that is 1. For rest of the time the value will be 0. So how to define this del of t now? Delta of t is the unit impulse function which has the value at 0. Its value at t equal to 0 will be always 1. So that means property can we write like this: minus infinity to infinity delta of t dt will be equal to 1 at t equal to 0. So if you integrate, what you will get? Delta of t, can take it as a constant at outside, so this will be cancelled out, so you will be left with del of t. If you put t equal to 0, so at 0 it will be 1. So this is the standard definition. Are you all following this?
Yes, sir.
Yes, sir.
Okay,
Yes,
Yes,
sir.
sir.
so since it exists at t equal to 0 itself, now if you take the what you say, the Laplace transform also, Laplace transform of delta of t, if we consider, so what we have to do, integration of 0 to infinity is there, right? And hence here if you consider f of t into e to the power minus st dt. Okay, so if this is the case, so then this will be 0 to infinity, f of t is delta of t. Okay, then e to the power minus st into dt. Okay, so since here if you consider, the Laplace transform definition is from 0 to infinity, but delta of t definition is from minus infinity to infinity. So minus infinity to 0, we don't, means there is no need to think about that, but 0 to infinity if you consider, so if you take the thing into consideration also, so then you will be left with what? Again this will give us the value as 1 only, because it is valid only for t equal to 0 only. Okay, So this is one case. So these are the simple cases. And now if you consider eighth one, which is very important here, that is exponential function. Okay, exponential function. So usually we have two kind of exponential function, one which is increasing with time and one which is decreasing with time. Okay, if a function is decreasing with respect to time, its exponential value is given by e to the power some value with respect to time, that is with negative sign, and which is increasing, that is given by e to the power 80. So graphically if you consider these two signals, they look like this. So with respect to t, if you consider exponentially increasing function. So exponentially increasing function means as you go towards the t value, so the amplitude should increase. It can be given like this or it can also be represented like this. Okay. Then what about exponentially decreasing function if you consider? So if you consider exponentially decreasing function, so that is given by as you progress towards the highest value of t, the value is going to decrease. Okay, so if you consider the solid lines here, what I have given, so this can be represented as e to the power 80, and this one is exponentially decreasing. Okay, so it is clearly visible here as you are going towards t, the amplitude is increasing, but here what is happening, if you consider amplitude magnitude here, so it is getting decreased as you are approaching the value of t, right? So usually decreasing function here we take them as exponentially decreasing, and this one is exponentially increasing function. So usually it is used in like distance or capacitor charge, right? Current through inductor and all. Again, when capacitor is getting discharged and all, so you can consider this as decreasing function. Okay, so these are the notations. So here first one in that if I consider, so anyone you can consider, if I consider the first one as exponentially decreasing, or in some textbook they may give you exponential decaying signal also. So in that f of t will be what here, f of t will be e to the power minus 80. So this figure should come in your mind. Okay, so Laplace transform of this will be what, this will be nothing but 0 to infinity. In the place of f of t I can put e to the power minus 80, okay, dt. So if you solve it further, so you can club, since the base is 1, I can write e to the power s plus a dt. This is going to give me the integration as e to the power minus s plus a t divided by minus s plus a, minus of s plus a, with the limits 0 to infinity. Okay, so you can take out this 1 divided by minus s plus a outside. So here in the t place if I put infinity first, that will give me the value as 0, and if you put 0 that will give me minus of 1. So together, what you can say, Laplace transform of e to the power at, it will be 1 divided by s plus a. Getting this, everyone?
Yes, sir.
Yes, sir.
So similarly, can you calculate exponentially increasing function? That is f of t equal to e to the power at. Just and let me know, or so similarly here also you can consider the Laplace transform as 0 to infinity e to the power at dt. So here if you take common base, okay, so here what we can write is s minus a of t dt. So if you consider this now, as usual, if you perform the integration, you are going to get what now? E to the power minus of s minus a, then divided by minus of s minus a. Okay. So this in turn is going to give you the limits from 0 to infinity. So if you put uh, upper limit minus lower limit, so what you are going to get now? So you'll be getting 1 divided by s minus a. Getting this, everyone?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
So this is about exponential function. And similarly now, if you move slightly towards the different functions, I think this one, 8th one, now 9th one, if you consider cosine function. So if I consider the cosine function, so we represented like this, the wave which starts here. Okay, so that will be continuous. Okay, so if I assume that the magnitude is 1, sorry, amplitude is 1. Okay, so this f of t, if I assume it as a cosine function, so f of t is nothing but it is cos of omega t. Okay, so this is in general usually written as what? 1 by 2 e to the power j omega t plus e to the power minus j omega t, right? Okay, now if you consider Laplace transform of this, so Laplace transform of cos omega t, this will be what now? 0 to infinity. In the place of f of t you can put this 1 by 2 e to the power j omega t plus e to the power minus j omega t into e to the power minus st dt. Okay, so later you can take this 1 by 2 outside. Okay, and you can combine here e to the power j omega t and minus j omega t. Okay, so like this, so you can just multiply this with here, so we can write integration of e to the power j omega t into e to the power minus st dt, okay, plus 1 by 2 integration of 0 to infinity. You can write this one with respect to e to the power minus j omega t into e to the power minus st dt. So overall you may take 1 by 2 as common factor, okay, and you can integrate again e to the power. Now you can take this t as outside value. So if you take that, I can write like this: minus of s minus j omega t dt, plus you can take again 0 to infinity e to the power minus of s plus j omega t dt. Okay, so this will be minus s, okay, that is fine. Okay, now if you use the exact values here, what it yields, okay, so that is going to give us e to the power minus s of j omega t divided by what you get is minus s minus j omega, okay, then plus here also with respect to 0 to infinity. So here you will be getting e to the power minus s plus j omega t divided by minus s plus j omega 0 to infinity. Okay, so finally if you use this infinity over here, so what we get is 1 by 2. So e to the power minus infinity, that will be 0. So you can put 0 there, or you can neglect that. Then what we get is minus of this minus will be plus. So I can write 0 plus 1 divided by s minus j omega. Okay, plus again you can write this first quantity will be 0 plus 1 divided by s plus j omega. Okay, so 1 by s minus j omega and 1 by uh, s plus j omega, that is going to give me 1 divided by 2 1 s minus j omega plus 1 by s plus j omega. So if you continue this further, this is going to give you 1 by 2. So if you cross multiply, that is going to give you s plus j omega plus s minus j omega whole divided by s square. That is, here we have a minus b and a plus b, a square minus b square. So that will be s square of j omega whole square. Okay, and this is further going to give me 1 by 2. Then these things will get cancelled out. You will be left with 2s divided by j square is minus 1 in complex uh, conditions. So this is going to give me s square plus omega square. So 2 and 2 will get cancelled out. So what you get is s by, okay, so this is the Laplace transform of cos omega t. Okay, getting this? Yeah, is it clear now, everyone?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Similarly, you can consider for the sine signal also. So for sine wave, you can have, now sine wave will start from 0 like this, we know. Okay, so if you consider the amplitude to be 1, so with respect to this, now f of t, what I am considering, that will be sine omega t. Okay, but sine omega t can be given as 1 by 2j, right? You can write it as e to the power j omega t minus e to the power minus j omega t divided by 2 times j. Yes or no? Okay. So now similarly, if you consider this for Laplace transform, so Laplace transform of this will be nothing but 0 to infinity. I can write then, so I may write this 1 by 2j outside here, and I can consider e to the power j omega t minus e to the power minus j omega t multiplied by e to the power minus st dt. So if you solve it further, that is going to give you 1 by 2j, then integration of 0 to infinity directly here, that is same way as we combined in the earlier problem. Here also can combine e to the power j omega t and minus st. So that is going to give you what? If you take t common, you will get j omega minus s, right? So if you take this one as s minus j omega of t dt, then here we have minus instead of plus, integration of 0 to infinity, here it will be e to the power minus s plus j omega t dt. Okay, then further if you solve it, so that is going to give you 1 divided by 2j. So this integration we know that is going to give us e to the power minus s minus j omega t divided by minus, okay, this is from 0 to infinity, minus e to the power minus s plus j omega t divided by minus s plus j omega. So 0 to infinity. Okay, so finally in the same way, if you further calculate, that is going to give us 1 by 2j. So first quantity here, if you put infinity, so that will be 0, then minus of minus, so that will be plus e to the power 0 will be 1, so 1 divided by s minus j omega. Then you will get minus of 0 plus again 1 by s plus j omega. Okay, so if you solve it further, so that is going to give you 1 by 2j 1 by j omega minus 1 by s plus j omega. So if you cross multiply and check out, so that is going to give you s plus j omega minus s plus j omega divided by s square plus omega square. So here you can cancel out these things. Okay, So you will be left with 1 by 2j into 2 times j omega divided by s square plus omega square. This will be 2j and 2j will cancel out. This will give us omega divided by, okay. So this is the required condition. Okay, following this.
Yes, sir.
Okay. So like that, if you go through the internet also, you may get plenty of standard results. So let us confine it to the required standard results only. Okay, so there are certain things. So something like one more, maybe the last one here, that is, if you consider exponentially again, exponentially damped signal. So what do you mean by exponentially damped function or signal? Any idea here? Any idea about exponentially damping? Damping means what? So if you have the signals like this, if you have the signal like this, what we called earlier exponentially decaying signal, right? Yes. So similarly, if you have a bunch of signals like this everywhere, so these are going to give you exponentially damping signal. So usually we take exponentially means initially it may have a higher value. So but as you go towards the time, so it may decrease. So if you plot that also, that is going to give you exponentially decaying signal only. So here we have the exponentially decaying function. So its standard definition is like this. So this is given by f of t is equal to Laplace transform of an exponentially damped function f of t. So we know already decreasing exponential function is given by e to the power minus at, right? So this if you multiply by some function, because it is not a single function. If it is a single function like this, then we could have written simply e to the power minus at. But it has some associated functions within that, right? So we don't know which function it is. So we can write this as e to the power minus at into f of t. Okay. So if you consider the standard result over here, so Laplace transform of e to the power minus at into f of t dt, it is given by, so again where it will start now, exponential function. So here we don't have the limits bounded only here to the first quadrant. It is applicable to first and fourth quadrant. So in the first quadrant and fourth quadrant, if you consider, so the value will be from minus 0, 0 minus to infinity. So if you consider this, limits will be given by 0 minus 2 f of t e to the power minus at into e to the power minus st dt. Okay, so if you find any of these kind of signals, so you can just write here e to the power minus at and st, you can combine it as s plus a, right? So if you combine that as s plus a, so we have the standard result that will give us Laplace transform of this will be f into s plus a. Okay, so we need to elaborate this with respect to sine, cosine as well. Okay, so for time being you just remember this. Okay, so we have discussed about around 11 functions, right? So after this we have to go to the linear properties of the Laplace transform. Okay, so till I start the properties of the Laplace transform, so all of you just make a note of all the 11 functions in this way. This table you continue what we have done. Okay, so after this we will continue for the properties of the Laplace transform. Okay, so take a minute and complete that. Okay, 50 are there. Yes, everyone make a note of that, those things. Okay, so we'll start the properties one by one. Aditya Nayak, are you on a call or what? Okay, everyone completed the given work, continued this. Okay, okay, now we will go through the few properties here of the Laplace transform. Okay, then after this we can go to the actual networks solving techniques. Okay, so second part of the introduction is we will go to the properties of Laplace transform. Okay. So first one, if you consider, first property is linearity property. Okay. So in linearity property, it states that if we have the two functions, if we have the two functions, that is f1 of s with its Laplace transform as f1 of s and f1 of t, not f1 of s, and f2 of t with its Laplace transform of f2 of s. Okay, then the Laplace transform Laplace transform of some constant multiplied by f1 of t, okay, plus another constant multiplied with second function f2 of t should give us a times f1 of s plus b times f2 of s. So how to do this? So just we have to prove it. So where a and b, where a and b, these are the constants. Okay. So if you consider now the overall Laplace transform, okay. So Laplace transform of a times f1 of t plus b times f2 of t, that is equal to integration of 0 to infinity a times f1 of t plus b times f2 of t into e to the power minus st dt, right? Okay. So if you split them one by one, so how we can write 0 to infinity? I can write a into f1 of t into e to the power minus st plus 0 to infinity b into f2 of t into e to the power minus st dt. Okay. So but if you look into the standard function of the Laplace transform, okay, so we can write like this: a is constant, this you can write it as f1 of t e to the power minus st dt plus b into 0 to infinity f2 of t e to the power minus st dt. So this is, it looks like the definition of the Laplace transform, right? This one and this one. So hence what you can write here: a into f1 of s plus b into f2 of s. Okay, is that clear, everyone?
Sure.
So it is just the property what we are discussing here. Okay. Okay, so next one, if you consider, that is second property. If I, okay, I could have written it here. Okay, now if I consider one more property, we will discuss this and we'll wind up anyway. Second one, that is called as time scaling. So let me write the function here first. So we know already if Laplace transform of f of t is equal to f of s, okay, then Laplace transform of time scaled function, that is a into t. So this should be given by 1 by a into f of s by a. So before going to the proof, let us understand the meaning of time scaling. Okay. So if I write something like f of t equal to f of 3. So in general, it means what? At time instant 3. Now, if I write instead of f of t, if I write f of 2t, so that implies what? F of 2 into 3, that will be 6. So the function which was supposed to start at 3, it is scaled by an amount 2 times. So that is nothing but it is going to start at 6. Okay, it may be a ramp function, or it may be a unit step function, or it may be a exponentially increasing function, or it may be a sine function, it may be a cosine function, any function which was supposed to start at these instant of time. Understood the meaning of time scaling?
Yes, sir.
Okay. So if you consider this over the Laplace transform, so how we can write for Laplace transform now? So Laplace transform of f of at, this can be given by, again integration limits will be the same, that is integration of 0 to infinity. Okay, f of t is now f of at e to the power minus st dt. Okay, so again it is not it cannot be solved directly, as we have the different variables, so we can use the substitution. So I can change, I can substitute at a of t equal to something like x here. Okay, then so with respect to this, what will be dt? Dt will be dx by a. Okay, so if you substitute it here, you can write Laplace transform of f of at equal to 0 to infinity f of x. So in the place of at, I can write x. So in the morning, we solved one property, right? So there also we have used the same kind of substitution. So here I can write, now I can put t is equal to what? X by a. So I can write s into x by a. Okay, then dx by a. So if you solve it 1 by a, if you take it outside, so you will be left with integration of f of x e to the power, I can write like this, s by a into x, okay, dx. So this is going to give me 1 by a, and already we know the integration of this, that is Laplace transform of this kind of function, where it has arrived e to the power minus at, exponentially decaying function. So there also, now if you further solve it, so it should give you f of s by a. Okay, So this is the second property what we have. Okay. So with this we will stop here now and we'll continue tomorrow. Okay. Thank you.
Thank you, sir.